Okay. In previous videos, we have discussed about motion, where we have discussed about uniform motion as well as non-uniform motion. So what we have observed that in case of non-uniform motion, there is an acceleration, and we were not talking about what is the cause of this acceleration. So now we will take into consideration the force which is causing the acceleration. So law of motion, here we are going to discuss, including these topics: Aristotle's fallacy, Galileo's inclined plane experiment, and the law of inertia, and then Newton's laws of motion and conservation of momentum. And then we will try to cover all these topics, including equilibrium of a particle. What Aristotle proposed, that if you want a body to keep in continuous motion, we need to provide an external force to the body. We need to push or pull this body consistently, or any kind of external force. So this is a kind of obvious. If you want a body to move, let's say if you want this ball to move on this plane, we need to apply some force. Okay, this is good, because we observe that there is a ball rolling on a floor. This ball will come to rest after some time or after some distance, and if you want to continue the movement of this ball, we need to push it, or we need to pull it. We need to apply a force on it. Okay, but what was happening in fact? In fact, we don't need to apply the force to keep a body in motion. If there is no force, and initially the body is in motion, this body will continue its motion. That should be a kind of uniform, continue its uniform motion, and if it is in rest, it will remain in rest. So this thing was proposed by Galileo. And now we are going to discuss Galileo's inclined plane experiment. And then we can state law of inertia. So what is inclined plane experiment? What Galileo did, he released a ball at one inclined plane, let's say at certain height h, and observed its height on other side. Let's say this height is s prime. So what he observed, that if we are releasing this ball from h height, it is trying to attain the same height on the other side of this inclined plane. This h prime is slightly less than this h. Okay, if we reduce the inclination of this second, let's say up to here there is one inclined plane, and after this there is second inclined plane. If we reduce the inclination of this second inclined plane, and we repeat the experiment, we release this ball from the height edge, so this ball travels more distance, but it comes to the same height as it was attaining in the previous one. So what we propose, that if we are reducing the inclination of this second inclined plane, this ball travels more and more distance, and it comes to rest only after attaining the height which is nearly equal to the initial height. Not exactly equal, it is little less, and we can say that why is it little less? Because of the friction. We know that we can't prepare any plane which is absolutely frictionless with zero friction. No, we can minimize up to some extent where we can neglect the friction, but absolute frictionless surface is not possible. So that is coming into picture, and that's why this height is slightly less. So coming back to the discussion, so what he proposed, that if we are reducing the inclination of this second inclined plane, and let's say we made it horizontal. Now this ball will keep going on unless it is getting the height h prime. Okay, but what will happen if this plane is horizontal? This ball is never going to get the same height, and then this ball is never going to stop also. So if this ball is initially in motion, it continues the same motion unless there is a situation which is retarding its motion. Actually, the second inclined plane is retarding the motion of the ball. What is happening in first part? Let's say in this part, ball is released from certain height at this inclined plane, and it is getting uh, what we call acceleration. And in second inclined plane, this ball is traveling upward, and then it is getting retarded actually. So the second inclined plane, which is causing retardation, if this plane is horizontal, means there is no retardation, then this ball will continue its journey along the same line. So this is what Galileo uh, proposed, that if we are not applying any retarding or resisting force, a body which is in motion will continue its motion, or a body which is in rest will continue to be in rest. Means a body wants to maintain its initial state. So we can say this statement: a body tends to maintain its initial state of motion or maybe rest, or it resists any change in its initial state. We can say this thing as law of inertia. And of course, this property of a body, this characteristic of a body, the characteristic of resisting some change in its motion or its state of its motion or rest, this characteristic or property, we call it inertia. So Galileo's inclined plane experiment and law of inertia, we can say that, okay, this thing actually no need to take into consideration now. Now moving to next point. After Galileo's inclined plane experiment and law of inertia, Newton proposed law of motion, actually three laws of motion, and we are going to discuss Newton's law of motion. Here we can summarize Newton's law of motion in a single paragraph, you can say. Let's say there is a body with some mass m, and if there is no external net force acting on this body will remain in its rest position or in its state of uniform motion. Okay, let's say this body is in rest. So if there is no net force acting in this body will remain in rest. Then what will happen if we are applying a force, a net force actually, on this body? So let's say there is a force acting on a body F. What will happen? Now there will be change in its state of rest. Now it may come in motion, and this force will change some parameter, something, and that we call, let's say this body starts moving along this direction with velocity v. So we can say, okay, now there is change in motion, and then this force is related to this change in motion. And how is it related? We can say after momentum, actually the force acting on this body is causing the change in momentum, and the rate of change of momentum is directly proportional to this applied force. So here momentum is nothing but, we are going to discuss these all things in detail. So momentum is nothing but mass times velocity. So we have discussed first law, that this body, if it is in rest or in uniform motion, it will continue to be in the same state unless it is experiencing some net external force. And if we are applying the external force, this external force will bring some change in its state of rest or state of uniform motion, or we can say this external force is going to change its momentum, and the rate of change of momentum is directly proportional to this applied external force. And of course the momentum change will take place in the direction of this applied force. And now third law, if a force is being applied on this body, there should be some agency or factor or another body which is applying the force. Let's say there is another body here, and this body is applying force on this body. Let's say this is A and this is B. So what will happen? This body B will also experience the same magnitude force, but just opposite to this force. That is, this body will experience the force in this direction. If it is applying a force in this direction on body A, the body B will experience a force in this direction. So this is the third law. That is the force. Actually, the forces come in pairs. Means if there is one body applying a force on another body, if there is one body applying force on another body, let's say a force F, this second body will also apply another a force of equal magnitude, but just opposite in direction. This is what Newton's third law of motion is. So let's discuss these all things in little detail. Okay. So here we have a statement for Newton's first law of motion, and we can say that every body continues to be in a state of rest or of uniform motion in a straight line. Means there is no change in direction of velocity also, unless compelled by some external force to act otherwise. Means if a body is moving along this line and then this line, and there is no force, no net force acting on this body, you can't say there is no force, because there may be some forces acting on the body, and those forces are balancing each other to give net force 0. So we can say there is no net force. So this will continue its motion along this side. Or in simple way, we can restate this thing, that if the net external force on a body is 0, its acceleration is 0 here, and then if there is a force, net external force, then acceleration cannot be 0. And if acceleration is not 0, there should be some change in its motion. There should be some change in its velocity. So that is what the first law of motion, Newton's first law of motion, is stating. Now, yes, I told earlier that we can't say that there is no external force. What does it mean actually? Let's say there is a block lying on this floor. So what is happening? If this block is at rest, not moving at all, what can we say? Whether there are no forces acting on this block, let's say we are on the earth, what can we say about the forces on this block? Whether there are no forces at all or there are balanced forces. So we can see here, if this block is on the earth, it will experience a force equal to its weight, and that force we already know should be mass times acceleration due to gravity. But what is happening? If this block is lying on the floor and it is in rest, it means there is another force which we call normal or reaction from this floor on this body, and these two forces are equal and opposite. So what is happening here? R is equal to minus mg. So again, net force is 0 here. There is no acceleration. Acceleration is 0. But we can't say that total means there is no external force there. So this thing we should keep in mind, that no external force and no net external force are two different, slightly different things. Yes, we have some external forces on a body, and they may result into net force 0. So this is what we are trying to talk here. Okay. Now moving to yes, there are several instances where we can see this inertia term actually. Of course, a very common example, if we are traveling in a bus and this bus all of a sudden starts accelerating, so we feel some kind of force in opposite direction. We suppose this bus is accelerating along this direction, so the upper body part of a person which is not in contact to the bus will move backward direction this way. So this is because of inertia. Okay. So moving to next point, Newton's second law of motion. Okay. Moving to next point, Newton's second law of motion. Okay. If there is force, this force is going to bring some change in motion. And now, what are those changes and how this force is related to those changes, we are going to discuss. So Newton's second law of motion here. What it states, that the rate of change of momentum of a body is directly proportional to the applied force, and this change in momentum takes place along the direction of the action of the force. Okay, the force is acting along some direction, and the momentum change will take place along the same direction. Momentum is nothing but let's say we are representing it by E, mass times velocity for a body with mass m, and if it has velocity v, we can say this body has momentum of m times v, and we can say that moment as okay, so we can say this body has momentum p, and we see here that momentum is a vector quantity actually. We can see here momentum is a vector quantity, and its direction, the direction of momentum is along the direction of the velocity, because mass is a scalar quantity here. So the only vector quantity in its expression mv is vector v. So the direction of momentum will be along the direction of vector v. So let's move to the next point. This momentum has importance actually. Why we are taking momentum? Because a moving body, if we are trying to change some momentum, if you're trying to change the state of motion, let's say, if you're trying to change the state of motion of a moving body, and then we want to know how much force we need to apply, this will depend on both factors, mass as well as velocity of the moving body. Now, why I am saying this? Because we can take some examples and observe what is happening. Let's say there is a body with mass something 1 kg. Let's say there is a body with mass 1 kg. This is the body, let's say 1 kg. And this body is moving downward with velocity of 2 meter per second. And there is another body of mass 2 kg, and this body is also moving downward with a velocity of 2 meter per second. Now we want to know, if we are placing some cushion here and some cushion here, which body will have more impact on this cushion? This body of mass 1 kg or this body of mass 2 kg? Well, these two bodies have same velocities. So which one will create more impact on this floor or on this platform? And we can say by intuition, we can say that if these two things are same, there will be more impact here. So what is happening? We are taking two bodies with same velocity but with different masses. So the body with greater mass will create more impact. And now we can change the situation. We can take these two bodies of same mass. Let's say these two bodies both are 2 kg bodies. And now we are changing their velocities. Let's say this body is moving with 2 meter per second and this body is moving with 10 meter per second. In second case, what is happening? This body is going to create more impact, not this. So this body is going to create more impact now. What is happening? We can't say that which body is going to create more impact based on its mass or its velocity alone. What comes in picture is mass and velocity. Both terms are responsible for this impact here. So if you want to try to stop, so if you want to stop these two bodies, we have to go for greater force in this case. Okay, let me clear it and we can discuss it again. So let's say okay, let's say this body has mass 5 kg and moving with a velocity of 2 meter per second, and this body of mass 10 kg moving with velocity of something 2 meter per second, let's say, and we want to stop these two bodies. So we know we need to apply more force here. Or we can change the scenario. We can take the masses to be same, 5 kg here with 2 meter per second, and 5 kg here with, let's say, 200 meter per second. And now we can say again, we need to apply more force here, greater force here, to stop this body. So what is happening? Elon mass or velocity can't decide how much force is required to change the state of motion. So we need to take into consideration both velocity as well as mass of the body, and that comes in the form of momentum of the body, what we have discussed little earlier. This is momentum, mass time velocity. Now the second law of motion states that this force, applied force, is directly proportional to the rate of change of momentum. And of course, the direction in which momentum change is taking place is along the direction of this applied force. So we can go for non-vector notation for timing so that it will be easier to calculate. So what is happening here? F is directly proportional to dp by dt, and being more specific, let's say average things. So F is directly proportional to change in momentum per unit change in time, or we can say F is equal to something constant, change in momentum, that is final momentum minus initial momentum. We can write here final momentum minus initial momentum divided by time taken to change in this momentum. Or we can say F equals to k times final momentum is nothing but mass into final velocity. We are taking mass to be constant. Just making one thing clear here. In this discussion, we are taking mass of this body is not changing. Although there are situations where mass is also changing in during the course of motion. Like we can take example of the motion of a rocket. So as the rocket goes higher and higher, it burns fuel, and that fuel was stored in the rocket itself. So after burning the fuel, the mass of the rocket decreases continuously during its motion. So we are not taking that thing here. We are taking mass to be constant, and then this will be mass times final velocity minus, for initial momentum, we can say mass time initial velocity divided by delta t, or we can say k times m times final velocity minus initial velocity per unit change in time. And we know this change in velocity per unit change in time, we can say this thing to be acceleration. So we have here force equals to mass, something constant, proportionality constant, k times mass times acceleration. And now we have to know about this k, or we have to settle it. And the best way to do, we if we can make this k 1, then it will be a very good equation here. We are going to get that now. So what is happening here? Let's proceed from here. F equals to something k into m into a, where m is the mass, a is the acceleration, and k is proportionality constant, which came after we did this thing. We remove the proportionality sign here. So if we are defining 1 Newton force, let's say 1 Newton force is the force required to accelerate a body of mass 1 kg by an acceleration 1 meter per square second. In with this definition of force, we have the value of k equals to 1. And if we stick to this definition throughout our discussion or throughout our study of law of motion, or everywhere we can say, then we will get F equal to m times a. And This is a very famous equation we all have come across. So this is the simple form of Newton's second law of motion. You can say that force, net external force on a body is equal to the mass times acceleration. And this acceleration is because of this force is being applied. So this is the second law. Now we can write in vector notation also. So we can write here vector A equals to mass is a scalar quantity times acceleration. And we can see the direction of acceleration is along the direction of force. So, and of course, this second law is consistent with the first law of motion also. Why? If we are going back and see what is the first law of motion we have discussed. So, we have discussed first law of motion that if net external force on a body is zero, then acceleration is zero. So, this is what we are getting here at the end. If we are applying no force, actually, if there is no force on the body, this F is zero, then M is a non-zero quantity for any entity. So A will be zero. And we can see this second law is consistent with first law with a special condition where the net external force is zero. Now let's discuss some more things about this second law of motion. Okay, so we have example from our daily life experience that while catching a ball, a player pulls his hand backward. Let's say there is a ball, and if someone wants to catch it, okay, uh, I think it will be able to catch it. So if someone wants to catch it, he or she has to pull the hands backward so that it can get more time to stop the moving ball. What is happening here? If this ball we want to stop in less time, means we have to change its momentum in less time. That is, there will be a higher rate of change of momentum. So to avoid this situation, what is happening here? If you are pulling your hands backward, you are giving some more time to change this momentum, and then the rate of change will of this momentum will be less. And for this less rate of change of momentum, you need to apply less amount of force. And as we know, if we are applying some amount of force on this ball will also apply the same amount of force, just opposite in direction on our hands also. So if we want to try to stop this ball and we don't want to hurt our hands, we have to give more time to stop this ball or to change its momentum from whatever is initial momentum while touching the hand to zero. And in this way, by giving it more time to stop, we are actually reducing the rate of change of momentum, and then we are getting less force applied on this ball, and in return this ball is applying less force on us. So this is the physics behind pulling the hands back while catching a high speed moving ball. Okay. Next thing is the direction of momentum and the direction of change in momentum. These two may are not same. What I'm trying to say, let's say there is a ball moving along horizontal path with velocity v, and then there is a force acting perpendicular to this velocity, or you can say acceleration is perpendicular to this velocity. So what is happening? Its momentum at this point, let's say at this point P, its momentum at this point is mv, which is directed along horizontal. But the change in momentum is not horizontal actually. this change in momentum is taking place at a right angle this way. The acceleration is along this way. That is the rate of change of velocity. Actually, v final minus v initial, we can say this thing, the direction of change of velocity and in terms the direction of change in momentum is along the acceleration, and this is not along its momentum. One more thing, uh, look, the force may act along any direction, but if we want to take the change in momentum along a particular direction, we need to take the component of the force along that direction. So now I'm trying to explain this thing by giving an example here. Let's say this is a block of mass n, it is moving horizontally, and if we are applying a force F, which is acting at an angle theta with this velocity vector, let's say this is also a vector quantity, force F. So if we are trying to get how much acceleration will be produced here, so the acceleration is not something F by m, because the entire force is not acting along the velocity. So what we need to do here, we can do one thing, we can just resolve this force into its component, and the component which is along this velocity will contribute to its acceleration. So the acceleration here along its motion will be the component. We can resolve this as f cos theta divided by m. This is the acceleration. So we can resolve the force acting on a body, and then if we want along a particular direction, what is the rate of change of momentum, then we have to take the uh, component of the force along that direction. Or if you want to know the acceleration produced in particular direction, we have to take the component of the force along that particular direction. This is what I'm trying to say here. So, okay, let's move to another point. Here we are discussing everything, and we are taking, suppose, a block we are taking. So, in fact, we are discussing these all bodies or all these systems, we are taking them to be a single point mass. Suppose I'm telling that there is a body of mass n, so I'm not taking its complete geometry, rather I'm taking this body to be single point mass. This all discussion This all discussion is based on this fact that we are considering a body of mass m is not a body actually, but a single point mass. And of course, we are going to discuss about the extended bodies also, or system of masses also. That that thing will come later while we will discuss about the moment of inertia terms and all. And one more thing, we are talking about these relations. These are local relations, means we are talking about a point. Okay, at this point, if force is F and this point mass has something value m, then at this point, the acceleration is something F by m. So for this particular point, we are talking about. Let's say there is another point P prime, and here there is mass m and force acting on this mass is F prime. So at this particular point, at this locality, we can say acceleration is F prime by m. And not to be confused, acceleration is a vector quantity, and this acceleration has direction along the direction of the force. This thing should be kept in mind. Okay, let's discuss about topic impulse. So impulse is nothing but force times time of contact. So this impulse we used to define for large force for short duration. This force is, you can say it's a large force, and this time duration is short. So impulse we can write I equals to F multiplied by delta t. Okay. Like other forces, this is also a force, but this force is acting for very short duration. If you want to get a physical example for this thing, let's say this is a floor or a surface, and a ball hits this surface and then bounces back. So Their time of contact is very short, and force is very large. If there is a large change in momentum, let's say this ball is of mass 1 kg and it is moving with a velocity of 200 meter per second, and let's say there is no deformation taking place, everything is in its proper condition actually. So let's say if there is no deformation taking place here, this ball hits this wall and comes back again. So what is happening here? Its momentum is being changed. Initially, it has momentum EI. Let's take downward direction to be positive, then we will take upward direction to be negative. So initial momentum, let's say, is 200 kg meter per second. As we know, momentum is nothing but mass times velocity. And final momentum we can take minus, we have taken the upward direction negative, and the final velocity will be in the upward direction. So this will be 200 kg meter per second. And then the force times delta t will be the final momentum minus initial momentum, that will be minus 200, that will be total 400, negative 400 kg meter per second. So this is minus 400 kg meter per second. Now, this is very difficult to calculate because the time duration is very short. So we have introduced another term where we can get force times time of contact, and that is nothing but the change in momentum. And this is coming from Newton's second law also, because force times this thing is nothing but change in momentum. And this is coming from Newton's second law. So in case of large forces acting for very short duration, it is convenient to use the term impulse. That's why we have discussed this term impulse here. Now, moving to next point, which is Newton's third law of motion. The statement we can say, to every action there is always an equal and opposite reaction. Or in a simpler way, we can say forces always occur in pairs. Now, let's take this scenario. Let's say there is a body, and now we are saying a body for the convenience, but the fact is we are taking point masses throughout our discussion. These bodies are nothing but point masses throughout our discussion. So let's say there is a body A and it is experiencing some force acting on it, external force acting on it, Fa. So this force is being exerted from some external body. Let's say this body is B. So what happens actually? Third law of motion, what says that if this body B is acting uh, on this body A with a force of Fa, the body A will also exert the same magnitude force but opposite in direction. What we are trying to say that Fa and Fb, B is the force acting on body B due to body A. These two are equal in magnitude and opposite in direction, or we can write very simple Fa equals to negative of Fb. So this is the third law of motion. These forces are coming in, occurring in pair actually. These forces are occurring in pair. Means there is force on body A, Fa, and this force is due to some body B, then there must be another force on the body B due to this body A, and that force should be equal in magnitude to this force Fa, but opposite in the direction. So this is what Newton's third law of motion says. Now, moving to next point, conservation of momentum. If we are taking both laws, Newton's second law and Newton's third law of motion, we can arrive at result uh, where we can say the total momentum of an isolated system of interacting particles, as we have mentioned that we are taking point masses here. So the total momentum of an isolated system of interacting particles is conserved. What does it mean actually? How can we arrive at this statement? So what is Newton's third law of motion? Let's say there are two bodies interacting with each other. Let's say this is body A and this is body B. these two bodies are interacting with each other, and due to body B, there is a force Fa acting on body A, and due to body A, there is a force Fb acting on body B, and this interaction is for delta t time. So, what is happening here? These two forces are equal in magnitude and opposite in direction. So, we can write Fb, let's say, is equal to F, then Fa will be equal to minus F. We are taking one dimensional problem here. The same argument we can extend to two dimensional, because we know we can uh, we can resolve a vector into its component. So if we are talking about motion in plane, we can resolve all those vector quantities which are involved in motion. We can resolve those all vector quantities along two different axes, making two one-dimensional problem. So Fb equals to minus Fa, and then we can multiply with the time of interaction, that is Fb into delta t equals to minus Fa into delta t. Okay, moving to next slide. So Fb into delta t, let me rewrite here. Fb into delta t equals to minus Fa into delta t. So Fb into delta t is nothing but change in momentum of body B, and this is nothing but into, yeah, Fb into delta t, and this is nothing but change in momentum in body A. What does it mean? The final momentum of body B minus initial momentum of body B here. So we can write final momentum of body B minus initial momentum of body B. Okay, we can denote initial momentum by F Ti equals to negative of final momentum of body A minus initial momentum of body A. And then we can write TFB minus TIB equals to minus TSA plus TIA. And we can transpose these terms, taking final moment of these two systems on one side and initial momentum of these two systems on another side. So we can write this thing as, now you can see our system is consisting two bodies A and B. This term is nothing but the final momentum of body B, and this term is nothing but the final momentum of body A. And if we are combining these two things, we are getting the final momentum of body A and B combined together. That is final momentum of system. And on the right hand side, we are getting in the same way initial momentum of the system. So by following Newton's second law of motion and third law of motion, and taking a system of two bodies, we are arriving at a result where if these two bodies are interacting with each other and there is no external force acting on these two bodies, their total momentum remains unchanged. That is, the total momentum remains conserved. Here we have the two bodies. So this is nothing but conservation of momentum. We can restate the thing that the total momentum of an isolated system of interacting particles is conserved. Here isolated system means mm, that system is not interacting with any external factor. Okay, so this is conservation of momentum. Now moving to the last point of today, last topic of discussion for this video, equilibrium of a particle. And what does it mean? Okay, here we are talking equilibrium in terms of force. So what does it mean? If there is a body, let's say there is a body, and if there is a force acting on this body, let's say this is the force acting on this body, F1. So there is net force on this body now, which is F1. But if there is another force of same magnitude, F1, acting from other side, so we can say now the net force on this body is 0. Because if we are taking this direction to be positive, then this force is positive, then this force we will take negative, because these forces are vector quantities. So this will be 0, null vector actually. So what is happening here? There are two forces acting on a body, and these two forces are summing to get net force 0. Means the body is in equilibrium. Why I am saying body? We are talking about point masses here. So even if I'm saying body or particle or system, we have to consider all these terms to be point masses. So not to be confused, even if I'm saying body, I'm saying particle or system, all these things are point masses. So let's say there is another situation, okay? And here we have three forces acting on it, or four forces to be easy, to make it easy. Let's say there is one force acting here, F. There is another force from this direction, which is also F. There is another force, F, and one more force, F. Now, this body has four forces acting on it. And then, if we want to know net force, we can say readily it should be 0. So, what is happening? This body is in equilibrium. This body is in equilibrium. In the same way, no matter how many forces are there, if they all add, look, here we are talking about the addition of a force. That addition should be vector addition. So, if there are many more forces acting on a body, let's say there are n forces acting on a body, and all those forces acting on the body giving net resultant force 0, then we can say the body is in equilibrium. So I can write a general statement here. Let's say F1 plus F2 vector addition plus Fn. If n forces are acting on the body is 0, we can say the particle is in equilibrium. So vector addition, we have to take care of this thing, that these all forces, if they are acting on a body and their vector addition is 0, we can say that the body is in equilibrium. In other words, we can say if a particle is in equilibrium, it means it has net force 0 acting on it. Means if there are so many forces acting on a particle and the particle has no net acceleration, then we can say the sum of all those forces is 0. And now we can take an example to describe this thing in a more clear way.